A group of students from UW Parkside set out to characterize the hydrogeology of the Kenosha Dunes in Kenosha, Wisconsin for an undergraduate research project. The purpose of this study was to get a preliminary characterization of the state natural area. Every year, more of the dunes are cleaned by Lake Michigan due to erosion. The dunes act as a buffer zone, protecting a wetland and the unique habitat that is home to rare and endangered plant and animal species. It is apparent that along with higher water levels in Lake Michigan, groundwater flow contributes greatly to the erosion here as well. The site lies directly on Lake Michigan, just south of the wastewater treatment plant. Parallel to Lake Michigan lies a series of wetlands which contribute greatly to the study. At this site, the flow of groundwater from the wetland out through the seepage zone of the dune face is being studied with two monitoring wells called Piezometer 1 and Piezometer 2. These wells each contain a level logger which measures the air pressure plus the water column above the sensor, and Piezometer 2 also contains a barrel logger which measures the atmospheric pressure above the water in a well. This area was created by receding glaciers. Exposure of materials left behind got eroded by wind and created the dunes. The bottommost layer is a thick gray clay which acts as the confining layer of the aquifer in study. Above this lies an organic peat layer that is remnant of the ancient Southport forest, which acts as an impervious layer. And above all lies about 4 meters of well-rounded, fine dune sands. The level loggers and barrel logger were set to read every 30 minutes, and data was downloaded and compensated 1 to 2 times weekly. Hand measurements were also taken weekly with the sounder. Depicted here are water levels with precipitation data obtained from a local precipitation station. The first peak of rainfall shows a direct and immediate response by the aquifer to that water that was introduced. This was expected after the second 2 spikes in rainfall, but due to a high water table, the barrel logger was found to be underwater and thus the data was not properly compensated. Overall, the hydraulic response is faster in Piezometer 2 than Piezometer 1, and the recharge response is also faster in Piezometer 2. Water level rises faster in Piezometer 2 because it's hydraulically up gradient of Piezometer 1. Water samples from the wetland, Piezometer 2, Piezometer 1, and the seepage were taken weekly and tested in the field for pH, temperature, and total dissolved solids. Samples were also collected in fluorinated sample bottles to be sent out to UW Parkside's S.C. Johnson Integrated Science Laboratory to be analyzed for a variety of cations and anions. Levels of sodium chloride decreased significantly from the wetland to Piezometer 2, which indicated that the wetland successfully filtered out these contaminants. The levels decreased slightly more from Piezometer 1 out through the seepage zone. Overall, this shows the importance of the wetland and its placement down gradient from a busy road. 4 samples were taken from the dune face to be used for sieve analysis. The wet samples were dehydrated in an oven and then poured into various grain sizes to evaluate the different grain sizes on the bluff. These data were compiled and used to create this grain size distribution graph shown here. The 4 curves are nearly identical, indicating very little variance in grain sizes. A majority of the sand fell under fine to medium grain sands, which is consistent with the expected soils of the area. This data was also used to find the hydraulic conductivity using the Hazen method, which yielded an average value of 7.56 times 10 to the negative 4 feet per second. Aquifer slug tests were performed to determine the water level's response to sudden rise and falls in the well. This was done using a rebar that was small enough to fit into the well. The rebar was placed just above the level logger, which was reset to read every second. The rebar stayed in the well for 5 minutes, then taken out. 5 more minutes passed after taking the rebar out to allow the water level to return to its static position. And then the level logger was taken out and the data was downloaded. Using the Horv's-Law method, hydraulic conductivity was obtained again. This method yielded an average value of 6.00 times 10 to the negative 4 feet per second. Hydraulic conductivity is a measure of water's ability to move through pore spaces. It is dependent on the type of material and its saturation, the density and viscosity of the fluid, and intrinsic permeability. An overall average hydraulic conductivity was determined from 2 methods. This value was found to be 6.71 times 10 to the negative 4 feet per second. This value is used in the groundwater model. An analytical groundwater model was constructed using Microsoft Excel using a rearrangement of the Dupuy equation, where h is the predicted height of the water table at any point x feet from the wetland, x is the distance from the wetland to the seepage, h1 is the relative elevation of the water at the wetland, h2 is the relative elevation of the water at the seepage, L is the length of the cross-section from the wetland to the seepage, K is the hydraulic conductivity, and W is the recharge. This model is a way to calculate the flow of groundwater through the transect studied. A visualization of the flow of water along the transect can be seen here. The seepage water table level was set at a relative elevation of 1 foot for all calculations, which was supported by a redox concentration 1 foot above the forest bed layer and the consistent observation of saturated sand just below this feature. The relative elevation of the wetland was set to 4.77 feet above the forest bed for all calculations due to repeated observation of standing water at this elevation over the course of the study. An equation was identified relating recharge rate to depth to water from the surface at piezometer 2, which was determined by trial and error. Recharge rates were calculated for each water level measurement to calculate the predicted depth to water at piezometer 1 and piezometer 2. Shown here is the predicted versus actual measurements. This graph helps to visualize the accuracy of the groundwater model. Since the depth to water at piezometer 2 was used to calculate the recharge, only predicted depth to water at piezometer 1 was used to test the accuracy of the model via regression analysis. The model was tested against 2,773 transducer measurements. The graph was made with measured depth to water of PZ1 on the x-axis and predicted depth to water of PZ1 on the y-axis. A linear trend line was added, and an r-squared value of 0.937 was obtained. The minimum, maximum, and average recharge rates were also calculated to be 0.018 feet per day, 0.053 feet per day, and 0.033 feet per day respectively. In conclusion, the chemistry data showed a decrease of sodium chloride from the wetland to the seepage face out to Lake Michigan. The wetland is important in the filtration of chemicals from road runoff so they do not enter Lake Michigan directly. The aquifers showed to have a direct response to precipitation. Between the two methods, an average hydraulic conductivity of 6.71 times 10 to the negative 4 feet per second was obtained, which helped create the groundwater model. The groundwater model proved to accurately depict the flow of water through the aquifer and gives a visual of aquifer recharge in real time. The observed versus actual depth to water helps support the accuracy of the predictive model. Overall, this study has been a big starting point in the Kenosha Dunes erosion problem. Today there are grad students at UW-Madison furthering this discussion in hopes to find a solution to protect this area. Thank you for taking time to listen to this presentation.